Good morning and welcome to this next lecture on sound and structural vibration. Last class we did a very basic introduction to waves and wave bearing systems. So we looked at some basic nomenclatures. Now before I move on to the actual problem, the first problem we are going to look at, I just want to add a few points that I missed in the introduction. Okay. So first point is that we said that P of x comma t is equal to f of Ct minus x plus g of Ct plus x. Okay. So let us take f of Ct minus x. Okay. Suppose I multiply within the argument a k. Okay. So this becomes f k Ct minus x. Okay. K is a constant. So in every derivative on the left or right of the wave equation, k falls out and cancels out, does not matter. Okay. Then what I have is f k Ct minus kx. K is the wave number, okay, and kc is omega. So I get f of omega t minus kx. Okay. So now if omega happens to be a single frequency, then this has to be written either as a sine omega t minus kx or cos omega t minus kx, or in a combined sense the phasor notation e to the power j omega t minus kx. Okay, that's one point I wanted to make. Then the second point is, okay, I said every point on a wave bearing system, vibrates, okay, sees the wave coming and going, and has a phasor description, phasor description. That means it has its own e to the power of j omega t minus kx. But I also said that everything is real. Okay. Finally we are interested in, finally quantities are real. Which means what? The expression has to be either a cosine omega t minus kx or a sine omega t minus kx. Okay. So in that crank and spring example, if I freeze time, or if we freeze time, okay, that means in these expressions we freeze time and then we move in space, then what? The expression is a sinusoid, right? So I will see a sine wave as I move in space. regions of compression, regions of rarefaction as a sinusoid. Okay. Similarly, if we freeze space, that means we remain in one place on the spring, some point x star. Then it will be oscillating also at the same omega, at omega. Okay. So the descriptor will be either some cos omega t minus k x star or sine omega t minus k x star. This is a constant now, right? So it's a cosine in time, sine in time. A single point will be oscillating in time as a sinusoid or a cosinusoid. So any way you look at it, the descriptor is sinusoidal. Okay, that's the second point I wanted to make. Then third point, I said many things about phase. Okay, I made points about phase. Okay. In actuality, if the system, that is mass and the spring, is driven by a force, okay, then of course the description, the response, let's say displacement, okay, will be, let's say displacement of the first point, okay, x0 will be omega t plus or minus some phase. Now it is phased with respect to the force. Okay, but because I was doing a schematic, okay, not an actual calculation, so I had my phasor starting at pi by 2, okay, and the mass was tied, hard tied, okay, with no flexibility to that crank. So I decided to give this mass also a phase of pi by 2. So we can do that, plus pi by 2, so that every next point will have a phase related to the starting mass. Okay, these are the points I wanted to make. Now we will begin a problem which I call as a classical problem in structural acoustics. Structural acoustics. Okay. This problem has been discussed extensively in the literature, okay, and mainly due to one author called D.G. Crichton. If you type this name, you will get the papers on any of the Google Scholar type sites. So what is this problem? It's a plate, okay, a flexing plate that resides in the xz plane, okay, it resides in the xz plane. This is x, that is z, okay, and this vertical is y. So there is this plate. It is an infinite plate. Extends to infinity in z, and it extends to infinity in the x direction, both directions. Okay, and above you have an acoustic half space. Acoustic half space. Okay, and there is a line force applied at x equal to 0 along the entire z direction. Okay, there is a line force, okay, applied, a harmonic line force. That means e to the power j omega t, line force applied to this infinite plate at x equal to 0 in the z direction. Okay. So by the very nature of forcings, all derivatives, all dependencies of z will go to 0. Okay, and therefore this plate becomes a 1D plate. 1D plate. Okay, so we can show the schematic in one dimension. So now what do we have? We have a one-dimensional plate with an acoustic half space. Okay, with a line force acting at x equal to 0, that is y direction, this is x direction. Okay, so the acoustic problem has become two-dimensional and the wave problem has become one-dimensional. Okay, now in sound structure interaction problems, there are two ways the problems are formulated. One is called the uncoupled formulation, okay, or also called one-way coupling, one-way coupling, or it is called fully coupled, or two-way coupled. Okay, so what is one-way coupled? So one-way coupling or uncoupled, formulation 1 is uncoupled, which is the structure is first placed in vacuum and it is forced. Okay, and the response that is displacement or velocity are found first with vacuum as the medium. Then the response is used to find pressures, acoustic pressures. That is, now the medium is brought in. Okay, so that means only one unknown at a time. Okay, there is one unknown at a time. The first unknown is, let's say, velocity, plate velocity. Then after it is found, the second unknown is fluid pressure. So this is one-way coupled. So why is it called one-way coupled? Because in this case the velocity that you have found does not change anymore. The velocity decides the pressure. Okay. The pressure in turn does not or cannot decide or modify the original pressure. No, that doesn't happen. Okay. So in contrast, we have number 2, the fully coupled formulation or two-way coupled, fully coupled formulation. What is that? The plate is excited and the plate excitations create pressure ripples in the fluid. So medium is already there, it is not vacuum anymore. So pressures are created. Now these pressures are immediately applied to the plate. Okay. So till a steady state is reached, both pressure and velocity of the plate are unknowns. So we have two unknowns, two simultaneous unknowns. Simultaneous unknowns. Both have to be solved together. So we will be looking at a two-way coupled problem now. Okay. So let's see. I have y direction, this plate, it's a 1D plate. Okay, there is a line force, medium. Okay, so the acoustic side variables, the acoustic variables. Okay, so rho 0 is the mean density, mean fluid density. Okay, c is the sonic velocity, sound velocity. Okay, phi x comma y comma t is the acoustic potential. P x comma y comma t is the acoustic pressure. Okay, perturbation pressure. Then we have P x comma y comma t given by minus rho del phi by del t x comma y comma t, and velocity, acoustic particle velocity x comma y comma t is given by del phi by del y in the y direction. Okay, we will be interested in the y direction velocities. Then K0 is the acoustic wave number, acoustic wave number given by omega by c. Okay. Now the Helmholtz equation. Helmholtz equation. That means the acoustic wave equation for a harmonic case, and the time removed is del square phi plus k0 square phi. If we open out, del 2 phi by del x square. This time is not there. The whole course is about harmonic excitations, not transients, and therefore I will often keep time and remove time in some convenient manner. Okay, it's cumbersome to keep carrying the e to the power I omega t type terms. Okay, so this is the Helmholtz equation. Okay, then on the structural side, we have E h cube by 12 into 1 minus nu square del 4 eta del x4 x comma z comma t plus twice del 4 eta x comma z comma t by del x square del z square plus del 4 eta del z 4 plus m or m dash. Okay, let's keep it as m del 2 eta by del t square is mass per unit area, x comma z comma t equal to 0. The configuration we said was such that all z dependencies will go, so this term goes away, so this term goes away, this term goes away because of the nature of the forcing. Okay, and so we are going to be left with, I'll give this a name called B so that I don't repeat it. So B del 4 eta del x4 plus m del 2 eta by del t square. This is my 1D plate. Okay. Now what are the plate parameters? E is the Young modulus of the plate material. Nu is the Poisson's ratio. H is the plate thickness. B is of course EH cube by 12 into 1 minus nu square is the flexural rigidity. Okay, then rho P is the plate density. Then M is the mass per unit area given by rho p into h. Okay, mass per unit area. Then eta x comma t, will take it as the plate displacement. Okay, and v of x comma t is minus I omega eta x comma t, because my time descriptor or the harmonic descriptor is e to the power of minus I omega t. Okay, let's see now. The force is given by F delta of x e to the power of minus I omega t, as it says applied at x equal to 0. Okay, and Kp is the Kp is the in vacuo flexural wave number and it's at a given frequency at omega, given by Kp is equal to m omega square by b to the power 1/4. Okay, then we have Cp is the flexural wave speed, given by Cp is equal to omega by Kp. Okay, and then we have B, plate equation B del 4 eta by del x4 x comma t plus m del 2 eta by del t square x comma t is given by f delta of x e to the power of minus I omega t. Okay, minus a pressure term at x comma y equal to 0 comma t. This is how the coupling happens. The pressure generated is applied back. Okay, now it's a linear system. So driven at e to the power of minus I omega t, the response will be at e to the power of minus I omega t. Okay, so eta of x comma t, I will take it as some w of x e to the power of minus I omega t. Okay, and my pressure x comma y comma t is equal to I omega rho phi x comma y comma t. Okay, so what I now have is B d4w by dx fourth e to the power of minus I omega t minus m omega square w of x e to the power of minus I omega t, that is equal to f delta x e to the power of minus I omega t, okay, minus I omega rho phi at x comma y equal to 0. I'll just leave it as a t, okay, that's also a harmonic term. So, or we'll write it as this, we'll write it as this manner, e to the power of minus I omega t, okay. Please get used to this shortcuts, okay. Actually phi x comma y and phi x comma y comma t are slightly different, but please, I don't want to keep changing notation. So this goes away, okay. So now I will replace w with eta for my own convenience, okay. So we get b d4 eta x by dx fourth minus m omega square eta of x is equal to f delta x minus I omega rho phi x comma 0. Now we have b d4 eta by dx fourth minus m omega square eta is equal to f delta x minus I omega rho phi x comma y equal to 0, and we convert eta to velocity minus I omega eta as velocity, so that b d4 v by dx4 minus m omega square v is equal to minus I omega f delta of x minus I omega rho phi x comma 0 is equal to minus I omega f delta of x minus omega square rho square phi x comma 0, in the kinematic boundary condition is given by VA of x comma 0 is equal to Vx, the plate velocity, which implies del phi by del y x comma 0 is equal to V of x. Okay, and this means at y equal to 0, this is plate velocity. Our time is up, so we'll leave it here for today.